Thank you. I'm currently pursuing PhD at Technical University of Berlin, and I work together with Ravi Shankar as one of my colleagues. Now he's working at Sintef in Norway. So usually we are doing a lot of research on mobile networks and devices for the last maybe 5-6 years, and we were always focused on mobile devices or mobile phones and or IMSI catchers or all this kind of stuff. So we thought, okay, this is kind of boring now. Let's switch the subject and let's find something new. That's how we started digging into or moving our focus onto base stations. Okay, this is something unexplored area, and then let's start digging into that. So that's how we came up with something called network automation. So recently, mobile networks have started implementing automation into their networks. So this talk is going to be what are the threats related to this network automation stuff and all this about. So basically, we are doing mobile network security. We were also interested in IMSI catchers and how they behave, or building such devices on a research level, and trying to dig more into telecommunication protocols and all this stuff. So the talk is going to be about, I give you an introduction about what is 4G LTE, maybe if somebody doesn't know, and what kind of automated operations are being performed in the mobile networks. And followed by this, I will present you the vulnerabilities and how we exploit them, and the kind of setup we used. And you will see 3 types of denial of service attacks in the whole presentation, and the kind of impact it generates, and the status of the vulnerabilities, with whom we disclosed, and what is the status now, and all these things. Also, I will end with some mitigations and nice takeaways for you. Before I start, I just wanted to give you an overview of how a mobile network architecture looks like. So this is a simple architecture. It could be referred to any kind of generation, maybe 2G, 3G, or 4G. So basically, there's a cell phone, there's a mobile phone, and there's a cell phone tower, and there's a core network. So the mobile phone is directly talking to the cell phone tower, and then this cell phone tower is maybe covering an area of 10 kilometers, or maybe even less, or sometimes 500 meters. And this base station is directly talking to the core network, where all the management or authentication or kind of security things are happening. So every mobile phone, when you turn on a mobile phone, it talks to the tower, and then it kind of authenticates with the core network, and then that's how you're being authorized or authenticated to use all the mobile services. If we talk about a cell is nothing but a geographical location divided into different sectors. For reference, they say it's in hexagonal shape. It could also be a different shape, but so cells are nothing but geographical areas divided into radio coverage. Something new which came up into LTE was the X2 interface. So the X2 interface, you see, that's connecting the 2 base stations. This is something new which came up in LTE or 4G. Because in 2G and 3G, there was no such link. And then if a base station has to talk to the other, it has to go to the core network, and then it's a long way. So, but here in LTE, to make automation or lots of features, they wanted to create a new interface, and then that's we call X2. Sometimes I also refer to the word called eNode B. It's nothing but a technical term for base station in LTE. Before presenting our attacks or all the vulnerabilities, I just wanted to recap the kind of attacks that happen in telecommunication infrastructure or telco in general. So this is the simple network. Okay, now I added the internet part. So the first one is, okay, IMSI catchers, also known as Stingray devices. Maybe it's quite possible that you could find a couple of them here or in DEF CON also. So basically, these IMSI catchers are trying to intercept the phone, or trying to get or collect identities of the SIM card or the mobile phone, for example, like IMSI, IMEI. Also, they can track the location of a mobile phone. So these are possible in all kinds of generations, like 2G or 3G or 4G. They are still possible in 5G also. So these are one of the well-known type of attacks and really used by intelligence agencies or, yeah. The second type is man in the middle, where a guy is sitting between or trying to relay the traffic between the phone and the base station. This type of attacks only work in 2G. Okay, they can also work to an extent on 3G, but 4G, you really cannot get useful information out of this man in the middle. Third one, interception. Okay, passive interception. So this was the attacker is passively listening to all the broadcast channels or all kinds of over-the-air traffic and trying to decode them. On 2G, it's really possible to intercept somebody's voice traffic. So this was already shown a couple, maybe several years ago. So the other type, okay, this is the quite famous and popular one, SS7. So the attacker, so SS7 is nothing but it's a signaling system which connects different operators or different cellular operators. There were so many vulnerabilities in the design of SS7 that attackers exploit to actually gain somebody's location or even track their calls or even divert their calls. Lots of things. So lots of things are possible with SS7 attacks. So for this, the attacker has to or should have an access to the SS7 interface, which is probably you have to approach an operator or somehow have some connection with him. The other is denial of service attacks. So here there are like compromised mobile phones which are trying to flood the base station or flood the core network with so many requests so that the radio channel is kept busy and other legitimate phones won't be able to access the radio channel. And in other case, when attacking the core network, they try to flood with so many authentication request messages so that the core network is also busy, and then this is kind of denial of service attack. So these things are well known, and then these are like quite addressed in the community. So just looking at these attacks, we can like say that the favorite target is always like mobile phone. It's really something very interesting because, okay, a person is carrying this one. But what about attacking base stations? Is this really possible without, I mean, I don't mean physically damaging or like physically plugging into the operator's network. Okay, this is something different. But is it really possible to attack these base stations without being detected? You could also say something like jamming. For jamming, you have to use a high power signal, and I think most of the operators have equipment that's really capable of detecting jamming or this kind of signals, because the signal is like super high power in order to kill the signal that's coming from the base station. So I'm not talking about jamming. So something else which we figured out was self-organized networks. So self-organized networks is nothing but all the network elements, for example, base stations or even core network elements, are automatically configured, controlled, and managed by themselves without the need of any human intervention. So this is the main concept of SON, self-organized network, and this is possible because of the X2 interface which came up in LTE. SON is actually a standardized protocol, standardized by 3GPP in the first release of LTE. So SON actually came into existence in 2009, 2010. So it's been already 8 years and nobody spoke about this thing because SON is something that's sitting on the operator's end. So normal people really doesn't have access to operator's equipment and they don't really know what's happening there. So it's hard to talk about these things. So here the base stations automatically configure and then control themselves. So when you reduce the human intervention, so the operators are able to save a lot of money. So it saves them like the capital expenses and even operating expenses. So if I tell in normal simple terms, SON is nothing but a software package which is either sitting at the base station. Okay, eNodeB is nothing but a base station. A software package which is sitting at the base station, or a central server which is controlling a group of base stations. If you look in the market, So there are different vendors. I don't want to name any vendor, but like we found different implementations from so many vendors. For example, Ultrasun or Elastic Sun or AirSun from different companies. And we found that 90% operators really, or the products really support SON, and it's up to the operators to really have these features activated. It's nothing but, I think, to me, it looks like just a button to completely make your network automatic, from manual to automatic. And there are no attacks reported till now. So this is something interesting, I thought, and then, yeah. So, and I just wanted to give you some background because SON is completely a bit different, new concept than what is mobile communication. There could be 3 phases of SON. So, SON, people say that. The first one is self-configuration. It's nothing but you bring the base station to the field, just leave it there, power it on, and then the base station automatically learns its surroundings. For example, discovers new base stations, try to connect to them because it has to find the IP address of the other base station. So it goes back to the operator network, try to get the IP address of the new base station, make a connection to that, share some configuration, and for example, like increase or decrease the coverage, because if it knows that, okay, this base station is handling this part of the area, okay, I don't interfere there, I have to configure my area in a different way. So this is how the base station configures itself. Also in this case, maybe a base station can have passive scanners that are continuously scanning the environment and trying to find if there are new base stations in the surrounding, so that their configurations can be exchanged and updated. In other case, there could be, not the other case, but the second case is like, there are cell phones everywhere, there are mobile phones like everywhere, and then these mobile phones are providing some kind of information to these base stations, like for example, measurement information or some new cells. Whenever the phone is scanning, it's uploading some kind of cell information to the base station. And the base station uses this and try to configure again, or if it finds a new cell, it tries to contact that and then make a X2 connection between that. So this is how even phones are helping that. So once the configuration is done, the second part is optimization, self-optimization. It's nothing but when the network is being operational, so it's doing a lot of procedures like handling calls, doing data, doing handovers, or so many operations. So all these operations are continuously observed and then try to optimize them. So this is nothing but a control system. I'll explain you the optimization process in the form of this diagram. So there is an SON optimization engine which is sitting on the base station or maybe a central server. And since it's a control system, it has some input and some output. So the input is nothing but coming from 2 different sources. One is internal. For example, let's say when the calls are being placed, so the call quality or all this kind of information is actually stored in the base station. So, or internal alarms, for example, when a call is dropped, so it means that the call failed, and base station stores some kind of information. Let's say 100 calls dropped, so which is really, it's not a joke, and dropping 100 calls. So these kind of signals or alarms are generated inside the base station and being used for optimization purpose. The second part is external, where the mobile phone is actually uploading some data. Also, it could be some signal information. For example, when you go into an escalator or when you go into an elevator, so obviously you lose or the signal quality is going down. So in that case, when the call is dropped, the phone would create some kind of report, like telling, okay, in this place, in this location, when I was connected to this cell ID, I had like this much of signal strength, so this is a failure report. And whenever it connects back to the network, it would just upload this information to the network. So network can use this and then try to troubleshoot some coverage problems and all these things. So lots of information is being fed into this optimization engine. But before that, there is something called performance analysis. So based on the success rate or the performance of the network, there are some key performance indicators. So if the performance is below a certain level, so it means that, or below certain threshold, the base station is really doing bad. So there should be something should be done there. So in that case, let's say like maybe there is due to lots of interference, or like due to overlapping of two different cells, there is lots of interference. And when there's lots of interference, obviously the signals drop and the connections drop. So when the KPI is going down, the optimization would initiate new configurations. Either it would decrease the coverage where the problem is, or increase the coverage, depending on what the situation is. So all this data is responsible for the generation of new configurations that are being fed into the LTE network. So the third phase, self-healing. So once the network figures out that okay, a particular base station has a problem, so now it's time to solve it. So there are different methods defined by vendors or implementations, so that the affected base station could be repaired and then again automatically repaired and then recovered and then again back into track. There could be 3 different modes of SON. It could be completely off, or if it's off, so the whole network is being manually verified, manually configured, everything. The second one, manual apply. So I found that this is also, with some operators, this is the case. With some operators, the automatic apply. So in manual apply, there is continuous analysis or like collection of the data, but to make some new changes, to make some new configurations, the operator has to manually verify or manually confirm that, okay, this is good, just proceed with the new configuration. The third one, this is a bit dangerous one. So all the analysis is automatically done and then new configurations are automatically applied. So this is a bit, maybe operators are a bit scared about turning on this kind of feature because it's a bit complicated, or maybe something could go wrong, just like demos. The actual issue we figured was like all the logic or all the intelligence that this SON is actually collecting is based on the information from different phones or all the phones and information that's shared across base stations. So we know that phones are super vulnerable and then they could be hacked and they are present in locations like over the air. And so there could be lots of problems with these phones. And the base stations or the SON is actually depending on the information that's collected from these phones. And without actually verifying them, it trusts that information and use it to actually generate new configurations. So this is some kind of design flaw we found, and then we wanted to exploit these things. So the key idea was like, okay, we have a LTE network, and then we have mobile phones, and then we have the base stations. And I showed you a bit of denial of service attacks before, where hundreds and thousands of compromised UEs like botnets are trying to attack these base stations. That's a different one. But now what happens, like if we place a rogue base station in such a scenario, like how does this react when there's a rogue base station in an automated network scenario? So we found different vulnerable points that could be targeted. For example, like how the cells are configured by base station. So this could be affected. Even the neighbor relations, like how a base station can actually connect with other base stations. So these things could be affected. Then handover analysis, because handover is one of the most important subject in mobile networks, because that's how we call it mobile. So these things can be affected. Also coverage enhancements, these things could also be affected. So to understand these vulnerable points, like I just wanted to share all the kinds of vulnerabilities we found in the SON. The first one is the Pci optimization. So Pci is nothing but a cell ID. So we have different cells. Let's say this is geographical area. And then each cell has a different cell ID. Because it has to be different, because so as to avoid interference between adjacent cells. When the network or when a base station figures out that, okay, the adjacent base station is trying to use the same cell ID like mine. So in that case, what happens is like the base station has to go off, not off, but like has to modify its configuration because it figured out that there is some kind of interference here. So this has to be done automatic. So the problem is like the base station is supposed to change its configuration by observing the surrounding base stations. So we'll see in the coming slides like how to exploit this kind of design or this kind of things. So if the base station doesn't change its cell ID, then there are a lot of problems happening. So there could be interference issues or handover failures. So for a correct operation of the mobile network, like it has to change its identity. The second one is the neighbor relations. Let's say there are two base stations and then the phones are trying to report the base station's identities to this one, and then this creates a connection between, this attempts to create a connection to the new base station. So once they are established or once they have an X2 connection set up, there is something called a neighbor relation table. Each base station is maintaining a neighbor relation table. So in this table, it has a list of all the neighbors or all the base stations that are in the surrounding. And then each has different attributes. For example, like no remove, no handover, or no X2. No remove, it means like this, the connection between these two base stations could not be removed, or it stays like a static. The second one, no handover. So it means like even though if they're adjacent, they cannot make any handover between them. Or the X2, they cannot have an X2 interface between them. So the configuration of these attributes is up to the operator. So he decides whether to have this or not. But the problem we figured out was like, there are no attributes or any kind of authorization elements to actually authorize the setup of an X2 relation. If you see here, like, so when cell A or base station A detects that there's a new base station, it would automatically create a X2 relation. But we would say like there is nothing to actually authorize this kind of setup, and this creates some kind of problem, and we see it in the exploitation stage. And LTE handover. This is the most important procedure, like I said. So let's assume that your phone, so this is UV, which is nothing but the phone, and there's a source base station, then there's a target base station. So the phone is actually in the connected mode. It means like, let's say there is an ongoing call, and the phone is trying to report some kind of measurement information like the cell IDs and their signal strings to the base station. And then let's assume that the base station is going close to a different one. In that case, the source base station actually talks to the target one, creates some handover procedure, and try to generate new keys, and then gives a command to the phone telling that, okay, now this is your new base station. So these are the configuration parameters, so just switch to that. And this handover command is actually based on two elements. One is the target cell ID, and the other one is a frequency. So with just two elements, like with just the cell ID and then a frequency, the phone is actually switching to a new base station. So assume that there is an attacker who is operating on this frequency and also trying to use the same cell ID. He will be able to actually hijack this handover because there is no other mechanism to actually, there's no mechanism for the phone to actually detect whether this is a real base station or whether it's a fake base station. We will see this procedure in the handover hijacking, which is coming in the exploitation stage. So the problem here was like all the cells or all kind of information that's being sent from the phone to the base station is not verified by the base station. Without verifying, it actually gives a handover command. So that's the problem we figured out. So we know there is an optimization phase. So all the handover procedure is continuously analyzed. So there could be different type of handover failures. For example, there could be an early handover or late handover or handover to a wrong cell. So these are different type of handover failures. And then like how does the base station identify a fault in the whole system? For example, like based on RLF report, like I said, I explained the situation of elevator where the phone is dropping the signal and then it's creating something called RLF report. It's nothing but a radio link failure report. So by the name, it means that there is a failure in the radio link and then it tries to create a report. Also, when the handovers are not happening properly, there are certain kind of handover reports that's being exchanged between the base stations. And the third procedure they use is like periodic KPI monitoring. So it's like periodic monitoring of key performance indicators. So these are the different ways how base stations identify faults in the network or in the handover procedure. So now, how the base station solves the fault? It would adjust the coverage settings. So this is one typical, like one usual procedure. And also there are like the success rates which define whether a base station is doing good performance or bad performance. For example, if the handover success rate is good, it means that, okay, this is good. If it's going down, it means that the number of handovers there are like so many handover drops. So this is not really good for the base station and overall subscriber experience, or it's not really good for the operator. So let's assume that there's a worst case where all the handovers are like all the calls are being dropped by the base station. So in such a case, if the KPI is going below a certain threshold, the base station can be handover blacklisted. For example, we saw in the neighbor relation table before that there is something called no handover procedure. So this option could be checked because the base station is really doing bad performance. And then so overall, the idea here is like how the attacker can exploit these kind of things. So he can actually inject some kind of malicious information into these reports because all these reports are going from the phone to the base station. So the idea is to like operate a rogue base station and then make an impact or generate rogue data into these reports, and then these reports are being sent to the base station, the legitimate one, and where we see like so many denial of service attacks happening. And the best thing is like the information coming from these reports is not being verified and it's being used blindly. So that's the main flaw. And I just wanted to repeat again that these are the different vulnerable functions, and these are some of the most important network functions. Without these functions, like you cannot really operate a network. So exploiting some self-organizing network features, you can really hit on some of the main functions of a mobile network. So now how do we exploit? So we made a setup because like in this case, we really don't have to, okay, like I said, we operated a rogue base station. So we really didn't have to operate a full-fledged base station. So it was sufficient to transmit just one broadcast channel. So it was okay to use some device called Lime SDR. I think most of you know this one. It costs like maybe $100 or something. So, and then we use a cheap PC because we don't have to do so much of operation here. Normally to operate an LTE stack, you at least need an i7 processor or at least something like this because it's really complex. But in this case, you don't really have to operate a full-fledged one. So the cost of the attack was like too low. And the other good thing is like you're not interacting with any UV. You're not the rogue base station is not actually interacting with any phone. It's just broadcasting a certain type of signal, a standardized signal, and then the phones are trying to read the signal, generate rogue information, and then forward it to the network. We tried this kind of setup with like within maybe 100 meters or something, and then we use some open source softwares, for example, like SRS LTE. And also for our testing, we got like, we collected maybe 3 or 4 different SON base stations and tried to perform our attacks and try to really study how these base stations are behaving. So we try to build our own a real SON network and try to operate the attacks on that. because you cannot do this kind of stuff on commercial networks. So, and it creates a lot of problems. So we could do it, but yeah. So, okay, how do we exploit the cell configurations or like the neighbor relations? Let's say there is an area with different base stations, and then each one is having a different cell ID. So, and then each base station has a neighbor relation table like I showed, and then this base station has actually its neighbors 122 and then the other one. So this is the neighbor, so it has this one listed in its neighbor. Normally here it makes sense to have an extra relation between these two base stations because they are adjacent and they can actually do handovers or exchange configuration. There is no point in having an extra relation between this one and then this base station because they are like too far, and then in reality they would never communicate because there won't be any kind of handovers happening between them. So in such a scenario, like if you operate a rogue base station that's actually spoofing the cell ID and the frequency of this base station. So what happens now? All the phones in this area would try to read this base station and then send measurement reports to the legitimate one. And the legitimate one reads that, and then what does it do? It tries to connect or create an extra relation with the base station that's far away. So the problem here is like, it's not authorizing whether to have it's not authorizing the setup of this X2 relation. So if you try to create, or like if you try to simulate different rogue base stations with different identities. So what happens is like each base station will have tens and 20s of different cells, and they are connected to each other. So this is like now a mesh network, which is not really the idea of mobile networks. So in such a case, like you have fake information here, and this could really cause handover failures, and then we will see it in the next one. So how do we kill and then remotely restart an LTE base station? So I told about this, the problem of operating same cell IDs with adjacent cells. So let's assume that there's a simple network here, and then with different base stations, and then there's a rogue one coming up with trying to spoof all these cells. So what happens is like, since this base station realized that okay, there is an adjacent one which is trying to behave like me, or like is trying to have the same cell ID like me. So as a property of the self-organizing network, the base station has to change its configuration. And this cell ID is a physical layer parameter, so you have to really restart the radio. So if you have to restart the radio, you have to like restart the whole machine actually. So it's not like an upper layer parameter or something. It's really a parameter that defines the radio signal. So we found in our experiments that some base stations really take maybe 7 or 8 minutes to make a restart. So during that period, because the base station is going off, all the cell phones which are connected to this base station are either handed over to an adjacent one, or they're handed over to a 2G or 3G base station if there is one in the surrounding. And then when the base station is connecting to 2G and 3G, so it's more vulnerable to different attacks. So this is one thing we figured out. And then the handover hijacking. So how do you take over calls? So this was a problem in 2G, or like INSI catchers were not able to or catch the guys who is actually on a call. So this was a problem in 2G and 3G. I found that, okay, this is something interesting and it's possible in LTE. I mean, in reality, it should not be possible in LTE because we want LTE to be a bit more secure than 2G and 3G. But unfortunately, it's possible to hijack or like to catch people who are already on an ongoing call. So how we do that? Let's say there's a simple network here, there's a base station, there's a phone, and then they are in an ongoing call conversation. So now what happens, like there is one guy with the rogue base station coming up and trying to spoof the cell ID of a base station which is a bit far away. But this guy is trying to simulate it very close to the phone. So now phone thinks that, okay, it found a new cell, and then it tries to report the cell ID and the measurement to this base station. So here it looks like the phone is actually close to the other base station, but in reality it's not. So, but this base station, what does it do? It creates a handover. So because it trusts the measurement reports, and without any verification, it tries to initiate a handover. So what happens here? This base station would start a handover process, but it's actually starting the handover process with a legitimate one. But the phone reported the signal from a rogue base station. So it creates the handover, then it sends a handover message to the phone telling that, so look, this is the PCI. PCI is nothing but 100, and then this is the frequency. So go to this new base station now. But the phone, instead of going to this base station, it would actually end up landing in the rogue base station, because it doesn't know like where it's going. So in this case, since the phone connected to the rogue base station, and the rogue base station doesn't have all the keys or the information to continue this call, so the handover procedure will drop. So it means that the handover failed, and it creates a radio link failure report. But the other base station, so which was the other base station, which was actually expecting this phone, realizes that something happened in between, and there was a problem. So now the phone and the base station both know that there is a handover failure. So it means that it's a problem of the mobile network, or it's a problem of the base station. And even the radio link failure report, if you look at here, all the identities are legitimate ones. So these are the spoofed ones, and the network has no idea whether this is a real report or a fake report. So this information is actually sent to the network. It goes to the network, and it will be used for the performance analysis, like the self-optimization procedure. So assuming like there are hundreds of handover failures being generated against one particular base station, and then let's say like there are 100 RLF reports with a cell identity of a particular base station. So it looks like that this base station is faulty one, or it has a bad performance. But in reality, it's not. It's doing good, but there is a rogue base station which is trying to impersonate that and try to defame the other base station. So like we said, if the KPI or the performance is going down a certain threshold, so the base station would be either blacklisted, or we found in certain implementations it could also be shut down because it's behaving bad and it has to go off, so that operator can replace this or offload this traffic to either 2G or 3G base station until he repairs this. So based on our experiments, like it's sufficient that maybe 5 seconds it's on one single base station. When there are like hundreds of cell phones around, it's sufficient that maybe 5 seconds you can drop all the traffic from a particular cell. So if you look the impact on a bigger scale, so on the subscriber, like there are lots of call and data drops. So this really affects the experience, the quality experience for the subscriber. And if the subscriber realizes that, okay, there are so many call drops, which is really not good for both the operator reputation and also for the subscriber experience. So in certain cases, we found that the phone is actually switching to 2G or a 3G base station. And then it makes it vulnerable again to a lot of different attacks. So on the operator side, okay, he knows, operator somehow realizes from these reports that, okay, there's a problem in that particular base station. So he has to send his repair and then, or remotely try to diagnose what's the problem in the base station. So there would be definitely like lots of customer complaints and all sorts of weird things. Based on our discussion with lots of operators, we found that there are no ways to actually detect if this base station is real or not. Because in this case, you're not really jamming and you're just operating a base station that looks like the other one. And you don't need like super high power or something. It's sufficient that if you're able to, if the phones in the surrounding are able to recognize your signal, it's sufficient to take or like perform all these attacks. And like even when the rogue base station is shut off, so it takes time for the self-organizing networks to come back into the normal operation, because like SON is kind of a control system, so it accumulates the performance for a certain period and then initiates new network configurations, assuming that the base station is off. And then so you can find like all the information about this, the paper and lots of work on this link. So we tried to communicate. We tried with different LTE phones and then different products, SON products, and then almost like all the products are being affected because these are not implementation problems, but these are mostly standardized problems. And then we reported these vulnerabilities, and then we discussed with lots of SON experts from different operators and also from European operators. And we communicated this to GSMA, and there was like very positive response, and they tried to really communicate with this with so many other operators. And there were lots of questions from them trying to see what can really go wrong with SON, and then why this wasn't fixed, or what are the mitigations and all this stuff. So one comment that some comments I received from operators was like, if they realize that if the attacks are going beyond a certain stage, they would switch the network to less automated. For example, maybe they would turn off the automation. This is one thing. Or in certain cases, they would unplug the defective base station, which is not really a defective one, but looks like, and then try to replace with a different one. And we also found that it's really difficult to add mitigations because of the design of the mobile architecture or the over-the-air communication. There's a lot of design flaw ranging from 2G also. And then we are in discussions with also GSMA wanted to create a document that's really that should be helpful for all the operators to tackle these rogue base station problems. So some solutions. So the best solution would be like to create authentication of these broadcast messages, because these broadcast messages are trusted by every phone, and that's how it connects to each base station. So once these are authenticated, but this is a very complicated solution, and it could not even happen in 5G for obvious reasons. The second solution we suggest is like do content verification. Whatever kind of measurement reports the phone is sending to the network, they should be verified, or verified in terms of the location of a particular base station, and then accordingly decide whether to take a handover or not just based on simple measurement data. And then add some kind of intelligence to the self-organizing networks, like see if the information that's being received from the phones is really authentic or fake one. Try to correlate this with some background data or pre-built databases that have exact locations of base stations. This could also be helpful. So the last solution we suggest maybe like have built-in baseband features. Okay, these are not existing even today, but we are trying to work with the vendor and trying to implement some kind of baseband intelligence so that can really help at least IoT from all the threats from rogue base stations. So some takeaways here are like we figured out that SON is something that's really useful and coming up for 5G also. So in 5G, I think there would be huge deployment of self-organizing networks. So, or small cells and even heterogeneous deployments. So it's really important to have self-organizing networks really ready to handle 5G networks. But the problem is like we have to fix the thing where the information received from or collected from different areas is not being verified. So this has to be verified. And also lack of appropriate parameters to take a network decision. I mean, like when you're changing the configuration of the network, it has to be based on several parameters, not just a parameter like a cell ID. So when the base station detects a new cell or detects a cell ID that's being impersonated, it changes its configuration. This is really not the right way to do the thing. So these things have to be handled. And then the last thing I would say, like a device like $200 rogue base station can actually modify network configurations, and then in certain cases it can turn the base station off. And this is something serious, and I'm happy that it's being handled in the right way in the mobile network community. So yeah, I'm open for questions. So thank you.
I have a question for you. Thanks for the excellent talk. Do you think there's anything that the app can be done at the Android and iOS level by the companies to help against rogue base station attacks on the UE end? Obviously not on the SON networks, but SON networks. Anyway.
Actually, all the data that's being exchanged between the base station or something, it comes from the baseband. So nor iOS nor Android does have any kind of control over the baseband, because baseband is the master of the phone, and we really doesn't know that. But opening access to this baseband would generate new threats and new things on the phone. So this is a bit of trade-off that the phone makers and then the baseband makers would really have to discuss, and then it's better have more intelligence on the baseband rather than having it either in the Android or iOS. So yeah, I would say it's more up to the baseband, not exactly the Android. We cannot do anything, yeah, actually on the Android or iOS side. Maybe having applications that can actually detect, for example, you know Snoop Snitch. These are some kind of applications that can detect IMSI catchers. They are not really accurate, but at least whatever is there, yeah. This is what we have now. So.
I'll talk to you later.
Yeah, cool, thanks.
So kind of along those lines a little bit. So from the user perspective of the phone, I guess from the data protection piece. So right now we're kind of looking more at like a denial of service issue, mostly for the users. Do you see, or have you researched into?
Could you be a bit louder?
Sorry. Yeah, I'm more concerned. I'm more concerned about the loss of data on a personal device. The denial of service is obviously could be a big issue if you're looking at a large set of cells or something of that nature. But for a particular user, that loss of data, have you researched into that, and what are some of the possibilities you've seen there?
Obviously, like it would affect a lot of phones. I mean, I won't say that, because if you look at the base station, it's such a simple thing. It affects all the cell phones in the area. So there is nothing that's really targeted against one particular user. This is targeted against all the. It's targeted mostly on the base station to affect that. So not
so much of a you wouldn't see this as a kind of a man in the middle for a large scale then.
No,
okay,
no.
Okay.
This is more affecting the base station part. So
okay, thank you.